All right, I can't see them from there, so I'm going to come over here. We're switching gears. We get to talk about how this is done. The code is provided on Google Collaborate, and partway through the discussion, I'll have you open that up. Video walkthroughs are available. You don't need to watch them. They were produced as we were vetting all this material, but they're there for your use after the fact if you want a refresher. You can also run the code on your own computers locally. It will be much faster, but not for today, but in the future. Okay, so my background, surprise, is not sheaf theory. Yay. Why I say yay is because I'm feeling you. These discussions were made with a lot of back and forth between myself and Michael. As you know, like I would like plug him and say, hey, that doesn't make sense, whatever. And so there were many, many slides that you will never have to see that he wrote, because I was like, that slide does not make sense. You should get rid of it. Just get rid of it. And so we reworked them. So like, hopefully this whole presentation makes sense to someone who didn't start out with sheaf theory in the first place. Okay, so examples. There's going to be 3, and we'll go through them. Okay, first of all, the first example, I wanted something so basic that everyone saw it in basic statistics. So how would you take just linear regression? How would you just do that with your sheaves? And so here's an example that if you want when you do your breakouts, you can try to recreate these points with that regression line. I just literally stole that off the internet. Okay, but for my example for right now, I'm going to use like trademark world's dumbest regression line, because it obviously is y equals x plus 1. And so I want to do this repeatedly in these examples. I want to create an example that I already know the answer to and make sure that my model works and make sure that the sheaf is giving me back what I expect. Then later, I try it on a more complex problem, like 8 points, see if I get the other line back out. Okay, so he did say this. Maybe it went by too fast, but he did say we need a directed acyclic graph. So we have nodes, which are like the points in your graph. And then you need the arrows. I'm calling those arcs. If it's a directed edge, I'm calling that an arc. And no loops. The nodes are going to have sets on them, and he called them stocks. Those arcs have to have functions on them, which he calls restrictions. And you basically need path independence until later when I violate that, but we'll get there later. Okay, so you need all these things mathematically in order to be considered a sheaf. So here's the first easiest example just to get it set in your head. Let's say the nodes are A, B, and C. And we're going to put real numbers, like the set of real numbers goes on A, B, and C. The edges are functions, just some function, some polynomial. So if I want to go from A to C, I multiply everything by 2, but I still end up with the set of real numbers. Then from C to B, I just add 17. I'm still in the set of real numbers. But if I want one thing like a restriction, I want just one valid solution. I could say A is 4, then on C I would have an 8, and I can't add 8 and 17. Whatever that is goes on B. Okay, so far so good? Okay, so some caveats. Some of your data will end up baked into the sheaf, which was a surprise to me. I would expect to put the data on after the fact, but you have to kind of challenge your notions of what things are and how things work and how the data flow, how the information flows in order to make this work. So, and for best practices, we're going to create the sheaf and then add the data. But in terms of programming, you can do it a little bit at a time. You can put some sheaf and some data and some more sheaf and some more data. That's okay. The program is fine. But all the examples I give you will follow the same exact pattern for best practices and for understandability. Okay, so I want you to imagine just a really simplistic overview. Let's say we have 3 cells. And this is to give you an understanding of what's happening under the hood inside pySheaf. So we have in the first cell, I'm cheating. The name of the data is D1, but the name of the cell is also D1. It's just this very high level discussion. If you have data on these 2 cells, but then you have 2 functions that tell you, okay, if I have data in that cell, it should come over here. It should cause D3 to happen. This is the data that should happen that flows off of that arrow. And here's the same path independence, right? These 2 things should be the same, and they should be the same as what we said in the first place. So inside his data structure, he's going to store what we think is in D3, what we think should be in D3 if we're coming from D1, and what should be here if we're coming from D2. And this is the thing that's going to get the distance measure. We're going to measure the distance from here to here and the distance from here to here. And that's the thing we're going to optimize over. Okay, so we're taking the model as it exists and looking at all those projections to see how they all fit together. Okay, so if we just, this is just symbolic stuff. Okay, if we take all those distances and square them and add them all together, we will end up in this instance with linear regression as we know and love. So let's build it. Now what? Well, we will have a directed acyclic graph regardless of which way we point the arrows, path independence, because this is such a simplistic thing. All we can do at first is maybe sit there on the paper and say, I'm going to have a model and it's somehow connected to my data. And in my mind, I'm thinking my data are my 4 points. That's my first attempt. And I'm like, how can I put them together? Well, then maybe I jot down, like, what do I know? Well, I know the stuff in blue. I know what the data are. I know what those 4 points are. And I know my line should look like y equals mx plus b. So m and b are the things I'm looking for. Okay, so your first instinct may be that the points, the nodes point into the center, but that's not actually going to be true. That was the first thing I tried to do. I thought that when I'm doing linear regression, each point somehow affects the model. But this sheaf idea, you should be flipping everything upside down in your head. Like try to explore and think about the implications of doing it the other way. It ends up that actually, as you remember that cell I had D3 up there? That cell is going to hold temporary starter information, your attempt, your initial guess. So what you're going to do is you're going to put an M and B in here, and you're going to use that to push out to your points, like what do you think Y should be in each of those 4 cases? So your linear regression line is going to be your prediction line, and you start with some garbage, any garbage you want. And notice how I wrote this. I wrote this star comma 2 to emphasize we only are holding the Y value here. The X value got embedded in the model. Why? Because when we're doing linear regression, we actually can't move the X's. They're not negotiable. It takes a while to think about that, but you know, if you're just taking basic statistics, you may think, oh, a best fit line is just like a geometric thing, but it's not, because the X and Y axis are completely different variable spaces. It's not a geometric line that you're looking at. One could be dollars and one could be gallons. They're not in the same space. So the X's are nailed down as something, and the Y is what you're trying to predict. So that's the only thing that can move. And so this is the weird thing. The sheaf is what's in red, and everything that's in blue is what we're going to call the assignment. Okay? So as we go through and optimize, we're not optimizing. The algorithm does, the pySheaf algorithm keeps changing MMB to see where it fits best. Okay, so here are the instructions. You're just going to use this for reference. You're not going to read the, well, we're going to read it, but you're not going to memorize it. You will now open up the first Google Collab, that's the LSR0. I want you to see that we go through, and I've marked everything in, and you see this is essentially 12 steps. A 12-step program. You guys got it open? Okay, so I'm going to just read from here, and you can look on your screen and verify that this is happening in the code. First, we load in pySheaf, and there's required dependencies. Then we call one or more sheaves into existence, and most of the time we're just going to call it SHF so that we don't forget which one it is, but you could call it anything you like. Then you're going to use either a default norm or you're going to define the norm type. So for this example, we're using L squared. I'm sorry, L2. We're going to square the differences and then add them together. So that's what we're going to be doing. Then we're going to add in all the cells into the model. Should we pull up the Google Collab slides? Michael, do you want to, yeah, just drive it just briefly, and then we'll come back to the slides. Okay, so just as you scroll down, So let's see, here's the obligatory imports. So when you see this, you click, so go to the top. Let's just do it once to show them. Okay, yeah, just, well, no, it's 30 seconds. It's okay. That feels like forever. So you click that and it takes 30 seconds. It feels like an eternity. And then, so like we won't do the rest of them, but that's okay. You'll do them. And then you can click. I think it's already pre-executed, right? So you don't have to redo it. But when you're on your breakup groups, you're going to want to do that. And you click, click, click as you go down. And you can, if you have a Google account, you can save a copy into your own Google Drive.
So I'm still hung up on the norm type. So the default norm is max, and then 2 sets it to the.
This is the one we're going to be using a lot. The default norm would be just the max. So like, in other words, it would be a difference, right? Like if we had. If you want to raise it to some other power, change it. That's fine. It's just the exponent. Yeah. Okay. Okay, back to the slides. Can I drive back on the slide? Oh wait, yeah, one more question. Go ahead.
Yeah. Could I ask a question about the acyclicity of assumption?
Yeah, not right now. Yeah, it's a high level question. Low level right now. Yeah. Okay, so. Yeah, back to the slide. So you'll just see that there's comments there to tell you what is happening as you go through. You're going to put in the cells, and then you're going to add the cofaces. In other words, those arrows are defined next. And then optionally create a sketch. I really don't like the utility for me because every time you execute it, it gives you a different picture. And I don't like that. But that's okay because it helps you check for typos to see that you connected everything you meant to. And I found typos that way. Then you place all the remaining data on your cells, all the cells. So at that point, everything has data, even the ones that you're looking for. So for example, M and B, they have some bogus data thrown in there. And maximally extend, what does that mean? We'll discuss what that means later, but it doesn't matter. You call the function that says maximally extend. In this case, if we have this star shape where you have only one node in the middle and they're pushing out, you only have to maximally extend that center one. But if you just want to be safe, maximally extend everything. Why do I not have control? Okay, we're good now. We're good. And then 9 is you check the consistency radius to see what it is before you do the magic. All right. And then you set optimization cells. So in this case, we say we're optimizing the M and B, but they're bound together. They're on one cell, and you're optimizing them together. Okay. And then you do the thing called fuse assignment, which is where all the magic happens. That's where pySheaf does all its optimizing. And then finally you come back and say, okay, what's the new consistency radius and what are the new values on those cells now that everything's been properly optimized? Okay. So that's just the 12 steps we're going to always go through in every example. So here are the results. And if you want to, you can look on your Google Collab sheet and see that this is what's happening. We started with the optimal solution to make sure we didn't have any typos and that we know what we're doing. So started at 0.707. That looks suspiciously like the square root of 2, maybe because it is. That's 1 over the square root is typical. Okay, so A, B, C, D, we're not allowed to change. Those were the Y values that we said originally were in our model. Remember the X was like 0, 1.5, 3 or something like that. The X values couldn't change, the Y values couldn't change. And you see that this actually stayed optimized, which is what we wanted. Okay, and the consistency radius did not really change. A little tiny bit change maybe, not really. It didn't really change. Okay, now let's change. And honestly, I don't even remember which is the slope, which is the intercept, whatever, who cares? I don't really care. But anyway, we had a bad consistency radius, bad meaning it wasn't optimized. And here's it. We just go ahead and run the program, and we get back to our optimal solution. Yay, happy. And back to a lower consistency radius. And we verified our very first example. Okay, any questions on that one? Yeah.
So maybe that's part of this is part of the reversal that you're asking us to do. So instead of like starting with the data and then modeling, like creating a model first and then packing in data. But maybe can you tell us why is it best practice to first create the sheaf fully and then fill it entire with data?
Well, in the programming structure that it is, you can't actually do it the other way.
Oh, okay.
But it's best practices also. So, but that he can address. But you can. The point is, if you want programming, you can add a piece and then put data to it, and then add a piece and put data on it. You could do it that way. That's fine.
Okay,
You can adjust it as you go.
Okay.
Okay. So one thing you can do.
Sorry, could you, I didn't really understand what the consistency radius is exactly.
The consistency radius is, in this notation for what we're doing right now, we just took the sums of the squares of the differences from between the projection and the data, and we squared them and added them. That's it.
Okay.
And so it's very roughly equivalent to, if you know statistics, it's like the residual.
Okay.
But in here, the point is, all your cells that are being used as optimizing cells, you're going to have some data that you're currently guessing, and then you're going to see what it should be coming from those different directions, and you're going to try to minimize the distances, the differences there. That's what you're minimizing.
Okay.
Yeah.
When the consistency radius is smaller, it's better.
Yes, you're trying to get rid of the noise.
Oh, okay.
The smaller it is, the more perfect it is. And if there's a perfect solution, you might get down to 0.
Okay.
Right, so if these points all were on a line, you would get down to 0. But the points are not all on a line, so there's no
And you have
perfect line
residual.
that can fit those points. But if they were all collinear, your consistency radius would go down to 0.
Oh, okay. Oh, consistent radius is like. No.
It's like the residual in statistics.
Yeah.
You're reducing
Yes.
the residual from the model.
Okay, got it. Thanks.
Yeah,
Energy principle thing, right?
okay. Okay, next example. So if you may remember that some people went looking for the Titanic. It's a popular thing to do sometimes, but they were not as careful as maybe they should have been. And this vessel exploded, unfortunately. But one thing was going through my mind when I heard this on the news is like every country in the world has underwater listening devices. They should surely be able to collaborate and figure out where that thing was. So that's the premise for this model. So I'm going to pretend like this is the ship that exploded, and we don't know its position in XYZ. If you can see, this is in light blue. If you think it's light blue. And the time, we don't know when it exploded. And also, we don't even know the speed of sound in this medium. Who cares? But let's just make the simplifying assumption, which is false, that within the region, that sound will propagate equally in all directions at a certain speed. So it's a simplified model. And then the green stuff tells me what each sensor heard when, because the sensor knows where it is and when it heard the pulse. That much it knows. Those 6 sensors collaborate to reverse engineer the location of the Titan and the time it exploded and the speed in the medium. And I made the speed just 2 because I made these all actually use Pythagorean theorem, so it's all integer solutions, because I wanted something that would be really easy to backtrack and make sure the model worked. Okay, so yeah, we know the 6 sensor locations, the pulse arrival times. We don't know these other things. And we use functions to predict the pulse arrival times, and I will spare you those details, but they're in the code. All right, now, first we check known solution stability. I put in the correct solution because I did it wrong 5 times in a row, and then just decided, let me just put in the solution, and then I found my typo. Okay, so that's why you start with the answer so you can find your typos. And then I found that I had a very low consistency radius even after I ran it. So it means it was stable, like it would stay on a solution if it finds it. Good. And then I just knocked it off and I moved the Titan away from the original location where I was guessing. I changed the time of the explosion and the speed of sound in the medium just as an initial guess. And it came back to the correct solution through this process. Okay, so yay, we found the Titan. Questions? that cool? Yeah.
The direction, you say direction, that's really direction in space, right?
Yeah,
The
three-dimensional.
first is, yeah, the first is like 2-dimension
Yeah.
because it's data distribution. So, okay.
Well, it's actually 1 dimension in the other one because I'm only looking at the y distance.
Ah, yes, yes.
So I'm trying to slowly ramp up the complexity of the model. Okay. How far away can we stray from this solution? So this one worked, but if you go far enough away, it stops working. And that's something we need to know. We're not going to spend that much time talking about it, but I will keep reminding you that this doesn't work forever. You cannot be infinitely far away from the correct solution and expect to find it. Okay, and that would be like way too much to like analyze, especially since each one of these problems is different, right? But just be aware that you can't be infinitely far away from your solution and expect to find it. That just know that much. Okay, so later, if you want, you go back to this code, which is example 1. Why did I start with example 0? What does that mean? What language are we working in? Yes, where does Python start? Yes, it was to remind you that Python starts counting at 0. Okay, one last example, hunting for foxes. Our family loves hunting for foxes. No, it's not because we're like Republicans with guns. It's not like that. It's not really that kind of fox. When we say fox hunting, we mean we're looking for amateur radio transmitters. That is my son Edwin's call sign. He's 18. And you'll see that he was probably about 10 or 12 in that picture. And so Michael is KB1DDS, I am N2SZ, and we like to go hide and each other can find us. And sometimes this is a formal game, sometimes it's just our family going out playing around. We have 3 cars, so one of the cars hides and the other car tries to find the other car. It's like a lot of fun. Okay, so the model is, oh yeah, Michael's father is also a ham. So yeah, it gets interesting. Okay, so we're just gonna do this in 2 dimensions because even though we have tricked Edwin by putting the fox up on a building that's a short shed, and he couldn't find it, he was looking around, he's like, it's right here, and I can't find it, and it was right above his head. But assuming that's not gonna be your fail, assuming that you're gonna hide the fox in a 2-dimensional plane, and some of your sensors can only detect the angle to the fox, and some of the sensors can only determine the distance. So if it's very loud, you know you're close. If it's very soft, you know you're far away. Okay, and some sensors can do both. And this is the first model where we're mixing. You may say, like, what does any of this have to do with qualia? But we're mixing different kinds of input into the same model. Well, we do have a problem then, because how do you know if a little bit of angle is more valuable than a whole bunch of distance? Like, what do? So you have to choose a weight. And I just chose a weight of 2, which that's not meaningful. It means in this situation, being off by 45 degrees is worth about as much as being off by 1.57 distance units. So you have to pick the ratio of the values of your 2 distances so that they can be combined in one model. And then you can just change that and see how it changes your stability. Okay? Okay, so we test it. I started with an initial guess of 2030, which wasn't right. The fox is at 1.1. And then I started with a consistency radius of 2.17. And I optimized it and got a really low consistency radius. And you can see we actually did find the fox as long as you consider 0.97 is close to 1 and 0.99 is close to 1. We found the fox. Okay, good enough for me. All right. So in this example, we held the values of the cells constant. They were not free to change. But in the angular distance, we're saying, like, when you're finding the fox, you know what you detected, but you don't know where the fox is. So one of the exercises I recommend in the groups is somebody takes the same code, and now you hide a different fox. So your fox becomes the thing that you don't optimize on, and you optimize on the sensors. Then you take that information, jot it down on a piece of paper, hand it to your friend. They find your fox. Cool. And so this is a really big strength of these models, is that you're using the same software to do the forward and the inverse problem. And there's not even a sense of forward and inverse problem because it may be partial. You may say, I don't know what this sensor is hearing, but I do know what this sensor is hearing. And I know the X dimension, but not the Y dimension. You can tell me anything you know and anything you don't know. It's not strictly speaking just a forward problem or just an inverse problem, but you can certainly make it a forward or inverse problem by just setting it that way. So it optimizes on anything you allow it to optimize on, it comes back and tells you. Make sense? It also will tell you when you fail. So I went and changed the weight to 20. So my initial weight was 2. And if you see, like the reason why these starting values are like this is 1.77. So the weight was 2 and now the weight is 20. So this is 10 times as big. And then this 4.49 is 10 times as big as this other 4.49 because there's no multiplier on it. So now it's times 10, which is accurate. That's what I wanted. I just blew that up. Guess what? We did not find that fox. No way, no how. The thing was just like spinning around like, I don't know where the fox is. You made that weight too big. Okay, so look at that horrible consistency radius. Nowhere near 0. Okay, and so there's a couple clues. One is that it went over, like our consistency radius that we started with is 21, and it went up. If your consistency radius goes up, you did not find anything. Sorry, you just got worse. You got stuck in a ditch. Okay, so sometimes your consistency radius goes down and you're still way off. And we will talk about that later in the next set of slides that I give, not his. Okay, so later, like I said, with a partner, you can hide a fox and then let them find it with the same code. Okay, so the summary concepts for the slides is your sheaf has to be built on a directed acyclic graph. The nodes contain sets. Functions take sets to sets along your arcs. Your assignment is one way to satisfy your constraints. Each cell has a set element on it as its data. Some data act as constraints, but others can be optimized. Forward and inverse problems use the same sheaf. Some data are baked into the arcs. The sheaf holds the current data and the functions as well as the predictions over which distances are found in order to calculate the CR. And that is it.
Okay, thank you very much. That was very cool. I would like to ask a question, whether a sheaf theory can actually maybe help with the inverse problem of the EEG.
Maybe.
Maybe.
It's a definite maybe.
Yeah.
What's the algorithm for the optimization of the
Actually, this is a good question. This is actually very, very cool. pySheaf uses the same API that scipy.optimize.minimize uses, and there is a nice little wrapper that you can drop in whatever optimizer you want. All of the examples use the standard out-of-the-box scipy.optimize.minimize SLSQP. Reason for that is because SLSQP supports bounds, which we will talk about. However, I've used pySheaf with other optimizers. In fact, rather fond of genetic algorithms. If you look in the pySheaf library GitHub, there's an example that uses the deep library for genetic algorithms.